So let's begin our look at rational functions. So rational function comes from the word ratio. Rational comes from ratio, and it is basically a function that is a ratio of two polynomials. And in math, when we talk about a ratio, we're talking about a fraction. So a rational function is anything that looks like this. F of x is some a of x over b of x. Doesn't have to be polynomials, but we're going to focus right now on polynomial functions. Generally, when we talk about rational functions, that's what we're talking about. So some examples of rational functions are f of x is 12 over x. So 12 is a function, it's just a constant function. The important thing is we have a fraction and there is an x in the denominator. If I just have a constant in the denominator, then I could just make that a multiple of a fraction and it's going to look like a polynomial. So I do need to have x in the denominator of the fraction, but I don't need to have it in the numerator. So here I have 1x plus 1. My denominator is x minus 2, 3x plus 1. Here I have x squared, or x minus 2 quantity squared over x squared minus 7x plus 12. These are all examples of rational functions, and that's what we're going to be spending some time looking at. So today we're just going to kind of get into some basic ideas with this. So what does one of these guys look like when we graph it? So we're going to start with the graph. And here is my function. I started with a nice one, f of x equals 2 over x minus 4. And if we graph this, we have something bizarre going on. Because you notice here, it looks like it's two separate pieces, and they don't look like they connect together. This is something that we haven't seen in any of our functions we've looked at before. So let's look a little closer at what's happening here. So I'm going to make an XY table. And I'm going to make, instead of y, I'm going to make this f of x. So if I plug in a number here, say 0, I get 0.5. And it's on my curve, because this graph should show points that work in this function. We'll go 1, 2, 3. We're following along there. 4, I got something's wrong. 5, 6, 7, 8, 9, 10. So as you say, we're kind of coming along fine, and then something funky happens at 4. So let's get a little closer to 4. So let's go here. 3 was okay. So let's go 3.1, 3.2, 3.3. We're looking good. 3.5, 3.8. Oh, 3.9. Well, I keep getting an undefined in there. Oh, I got 3.58. That's why. How about 3.99? How about 3.999? Hope I got an extra decimal point in there. So, as we go, here's our 3.9, and it just keeps going down and down, and it almost looks like it's going straight at this point. But again, at 4 we jump, 4 we can't be, at 3.999 we're at 2,000. Come on, hello. If I go 4.001, just the other side, now I'm at a positive 2,000. It goes down from really negative and it pops up to really positive. So it's doing that weirdness. And that weirdness is happening right at 4. What it is that there's kind of like... Well, let's come over here. It's kind of like where x equals 4, I have this dividing line. It's kind of like a wall. You're coming along at a good clip, and all of a sudden there's a wall in front of you, so you swerve to not hit the wall. And all of a sudden you're getting closer and closer to it, but you never quite hit the wall. You don't go through it. You just kind of get as close as you can, mathematically close. And the same thing happens when we're coming in this direction. We're coming down here, and now we got to swerve to miss it. And we swerve either down or we swerve up, but we don't ever get to that point there. We don't ever get to 4 because 4 is undefined. 4 is undefined because my function is 2 over x minus 4. And if I put a 4 here, 4 minus 4 is 0. I have 2 divided by 0. I cannot divide by 0. Let's look at a few other. If I look at this one, x plus 3 over 2 times x minus 4, x plus 2. I'm coming along here, and then I'm getting to negative 2, and all of a sudden, wow, I swerve. I got a wall there. X equals a negative 2. And then over here, I'm coming up from negative, if going on this way, I run into trouble at negative 2. Coming in this way, I run into trouble at x equals 4. These are my two kind of dividing line, and it breaks this up into 3 pieces because they don't cross, they don't connect there. If you look at this one, this one got all sorts of weirdness. But where is the weirdness happening? It's happening here at, looks like negative 5. It's happening over here at negative 1. It's happening over here at 4 again. What's special about negative 5, negative 1, or 4? Well, if x equals negative 5, this is 0, and my denominator is 0. I can't divide by 0, so I can't equal negative 5. Negative 1, this x plus 1 equals 0. At 4, x minus 4 equals 0. So where my denominator equals 0, that's where I'm having these glitches. Because I can't equal, my denominator can't equal 0. So take a second to think about this last one. 3x over 2 times x minus 3, x plus 2. Where do you think those glitches are going to be? We use the same idea. Where does x equal 0? X equals 3. X equals negative 2. Those are the points where this denominator equals 0. Let's see what the graph looks like. And here, those are the trouble spots. These lines, these vertical lines, which kind of split this, where we have our trouble spots, where the denominator equals 0, we call this a vertical asymptote. And again, that happens where the denominator equals 0. So, let's give some more definitions here. Our vertical asymptote. Let's do that. Vertical asymptote is going to be a vertical line. It's not actually part of the graph. We often use a dotted line to represent this vertical asymptote because it's not actually part of there, but it's kind of that dividing wall. We kind of imagine it. Like we often think of it like a curb or a fence. Why did this one disappear, but these do? I don't know. It's kind of like, we don't, like when we were parallel parking, you don't want to hit the curb. It doesn't ever hit there. It doesn't even hit the fence. It just gets mathematically as close as possible. But it just shoots up to infinity or shoots down to negative infinity. We find these by looking for where the denominator equals 0. So set the denominator equal to 0, solve for x. The equation of a vertical asymptote is always going to be x equals some number. So let's look back at our examples. We're going to look at these and say, where are my vertical asymptotes going to be? So my vertical asymptote is going to be where the denominator equals 0. Where does x equal 0? Well, I got to take it off the disappearing ink. Okay. Where does x equal 0? Where x equals 0. This is my vertical asymptote. For I look at g of x, I want x minus 2 times 3x plus 1 to equal 0. A little bit more to this, but it's in factored form. So I set the factors equal to 0. X minus 2 equals 0. X equals 2. 3x plus 1 equals 0. So 3x equals a negative 1. So x equals a negative 1/3. This one's going to have two asymptotes, two vertical asymptotes. Last one, we look at this one. X squared minus 7x plus 12 equals 0. Well, that's not in factored form, so let's see if we can make it that. If we come here, x squared and 12. So x is going to have to be x and x. I need two factors of 12 that get to 7. So that could be 3 and 4. Well, that's 4x. That's 3x. But it's a negative 7, so I'll make those both negative. So this is x minus 3 times x minus 4 equals 0. So my asymptotes are going to be at x equals 3 and at x equals 4. That's how we find our vertical asymptotes. Again, our vertical asymptote is going to occur where the denominator equals 0. It's an imaginary line that the graph does not cross. It gets really close, but when it gets close, it either shoots up to positive infinity or down to negative infinity. Then it jumps over that point where the asymptote is, because that's where the denominator equals 0. We can't have divide by 0. But when we jump to the other side, then we're approaching it from the other side. We have another swerve down either to positive or negative infinity. So those are our vertical asymptotes. So that's where we're going to stop this video.